In this section, I would like to give you basic information about this session. The purpose of this session is to introduce you STM32CubeIDE tool. Its installation process, we will focus on Windows platform, its basic configuration, and first run. During the first run, we will toggle one of the LEDs present on the board. The next purpose is to demonstrate to you the main components of STM32CubeIDE, device configuration, code processing, and project debugging. Within this session, we have prepared some set of examples using HAL, so Hardware Abstraction Layer, and Low Layer libraries. Let's talk about the prerequisites for this session. The first and most important one is, of course, the PC with pre-installed STM32CubeIDE software and STM32G0 Cube library. We have selected STM32G0 71RB microcontroller as to practice during this session. This is why this library is a key to allow us to generate the code and prepare some set of examples. From hardware point of view, you would need one Nucleo board. It is called Nucleo G071RB. You can see it on the screen. And one micro USB cable, which allows us to connect this board to your PC. Complete list of prerequisites and a link to all of the materials, slides, exercises, hands-ons, you can find on the dedicated web page for this session. A link to this web page I have put within the description of this video. More information about our other STM32 devices, other tools, you can find on a dedicated web page, which contains all the information about our training materials. You can easily find it on the web using this address www.st.com/stm32education, and within MOOC section you can have a look on a complete set of available training sessions. I will start from standard ST web page. This is our current ST web page. Let's go to mentioned web page with trainings. www.st.com/stm32education. If I will scroll down, I can see some additional icons which I can select. You can find here online trainings, which are theoretical trainings for all of our STM32 products. Let's have a look what we can find here. You can find here some set of online trainings, theoretical trainings for STM32F7, STM32L4, L4+, G0 and WB microcontrollers. Let's come back to our previous page. The other icons represent other areas which could be interesting for you. The next one is so-called MOOC, Massive Open Online Courses. This is the area where we place all of our online trainings, which contains some set of examples as well and hands-on sessions. Those are hosted at the moment on our YouTube channel, so it is quite easy access to them. If you click on this icon, you will see the dedicated page for our online courses. You can find here 5 different groups of trainings. Basics, STM32 tools, STM32 lines, applications, and tips and tricks. You can start from basics if you are new with an STM32 world. Then you can find some dedicated sessions about STM32 tools. Then if you are interested in STM32 lines like L4, F7, G0, L0, you have some set of dedicated training sessions of those microcontrollers. Then within applications, we are presenting some dedicated sessions on LoRa, graphics, motor control, USB, so dedicated areas of microcontrollers usage. Within tips and tricks, you can find some selected topics which could be interesting for you within microcontrollers world, like ultra low power handling, dynamic tools and in application programming or security basics. This list is quite dynamic. We are adding more trainings each month, so please visit it regularly to be up to date. All of the sessions right now are hosted on our ST Microelectronics YouTube channel. This page and its sub-pages, because here you can see the links to each session, contains main information about the session, its prerequisites, links to the materials which can be useful for you to do the session. So if I click on this STM32CubeMX training, you can see a dedicated page when you can find basic information about the session, its outline, its agenda, list of the prerequisites, software and hardware, and you have the link as well to access the course. If I click this link, I'm landing on the dedicated page with the playlist of this session. So you can see here under the video, I'm repeating the basic information about the session. You can see the set of videos for this particular training. Okay, let's start our adventure with STM32CubeMX. Hello and welcome on our STM32CubeIDE Basics training session. In this part I would like to introduce to you the board which we will use during this session. It is called Nucleo G071RB. You can find the name over here. It contains its own programmer debugger called STLink v2.1. This is this top of the board. Below you can find a dedicated board for the microcontroller. Our microcontroller would be STM32G071RB T6, 64-pin microcontroller from STM32G0 family. This is the central chip on the board. On the board you can see as well some additional components which would be useful for us. Some buttons, LEDs, jumper to measure the current consumption, some connectors which allows us to connect other components. Let's have a look on the components which you will use during this session. On top you can see the STLink programmer debugger. It can be connected to the PC using this CN2 connector using micro USB cable. This is the main chip for the STLink. Below you can find a board for our microcontroller with the microcontroller in the center. Blue button is so-called user button. It is connected to pin PC13. We will use it to test the external interrupts. The black button is a reset button, which allows us to reset the complete application. On board we have as well the green LED. It is located on the right side of the reset button. This green LED is connected to PA5. We will use it to indicate some states of our application. Once we connect the board to the PC using micro USB cable and this CN2 connector, a STLink driver will be installed on our PC. If the driver is properly installed, after the connection of our Nucleo board to the PC, we should see LD1 red LED on, which if it's blinking, it means that there is a problem with a driver installation or the board is not yet detected by the system. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this video, we will do the first hands-on. The objective of this lab is to create the project using STM32CubeMX and HAL libraries, which would allow us to toggle green LED, which is connected to PA5 pin on our Nucleo board. Here you can see the part of the schematic of Nucleo board which we are using in our exercise. Our LED is called LD4. It is green LED, which is connected to pin PA5, what you can see on the screen. Let's open the CubeIDE application. The first thing we need to do after run of this application is to select the location of the workspace. I would select a different name just to start everything from scratch. In my case, it will be C, then underscore work, and subfolder CubeIDE, but with number 3. I launch the application. As the workspace is empty, there was no project inside the workspace. It doesn't contain any project. We can see this Information Center welcome screen, and we can start a new STM32 project. So I select this icon. So the first thing is to select the micro we would like to use for our project. Take some time. So this is the target selection window. We have 3 options here. Either we will select the particular part number, Mcu Mpu, or we will select one of the ST boards which is equipped with STM32 devices, or we will select the cross selector, selecting some ST competitors, and I try to run similar project on STM32 devices. We'll select the Mcu Mpu Selector just to do everything really from scratch, and we need to select our micro. In our case, it is STM32G071RBT6, part of it, because STM32 is existing in all of the products. I'm starting from this G071RB. I can see one choice, RB. I'm selecting this part number. So we see 2 of them. We are selecting LQFP64 package, because this one is located on our Nucleo port. Once I highlight this number, I click Next on the bottom of the page, and the next step is to specify the project name we would like to create. Here you can see the default location of the workspace, and within this workspace we will have as well the location of the projects. I would call my project as a G0_LED, and I have some options to be selected. By default, it will be C project, the binary type it will be executable, and the project type it will be STM32Cube based. We can select as well C++, we can select the static library, which can be reused in other projects, and we can select as well the project type as empty. But in this case, we will have just an empty skeleton of the application, and we need to define our set of the registers, register map by ourselves. In our next videos, you will see the project generation using this empty project type, so you can follow this part as well. Let's continue with the project setup using STM32Cube. Let's press Next. On this window, we can see the micro we just selected, the version of the library we will use. So in our case, it will be Cube for G0 in version 1.2.0, and the location of this library. So in my case, it is C_work and subfolder _CubeMX. Below, you see as well the link to the configuration window, where you can configure the repository location for your libraries. In this window, you have an option to select the code generator options. So either you will copy all the necessary library files to the location of your project, or you will use it as a reference to the original files. We will use the default settings. Copy only the necessary library files. Okay, let's press Finish. As a result, we can see some information window about the perspective change. Within Eclipse environment, you can have a set of so-called perspectives. So this is the configuration of the Windows set, which is present on the screen. Within STM32CubeIDE, we've got at least 3 main perspectives. The first one is so-called CC++, which is used to edit the code, perform the compilation of the code. The second one is so-called STM32CubeMX or device configuration perspective. And the third one is a debug perspective, which is used to debug the application. So I would just click Remember my decision and Yes. So now it is starting device configuration part of CubeIDE software. In case you have not downloaded the STM32G0 Cube library, it will be done automatically, as you can see on my screen. So the application will connect to the repository, the web page. The proper Cube library will be downloaded as a zip file and then unzipped in the folder we just specified 2 steps before. we need to wait a bit to download and unzip the complete pack for G0 family, and we will continue. When it's done, we can see the screen similar to mine. In the central point, we can see selected microcontroller, all of its pins. Yellow pins are related to the power supply. Unused pins, free to use, are marked as gray, as you can see on the screen. The other colors means that the pin is already assigned as a power pin or some reference pin, as you can see on the screen. So the first thing we need to do to create our LED toggling application is to select and configure the debug pins. So I would go to the system core. I would select from sys peripheral serial wire. Serial wire, it's in fact SWD, serial wire debug interface, which is common to all STM32, in general Cortex-M devices. So once we select this interface, we can see that two pins, PA13 and PA14, are already dedicated to sys system peripheral SWDIO, SWCLK, so the debug interface pins. So this is the first point. The second point, we need to select the pin we would like to control. This package is not that big, so it's quite easy to detect PA5, it is over there. But if you will have bigger package, some BGA, where there are a lot of pins, very nice way to detect the pin is to use the search field on the bottom of the screen. I can type here the pin I'm looking for, so PA. Now you see all PA pins are highlighted. I'm selecting PA5, so it is over here. I'm clicking left button on mouse and selecting GPIO output. Okay, now pin is selected by me. This is why I can see this pin over it, and it is green, so it is selected. It is it has some role assigned to it. Now I can assign as well the label to this pin to have easier access from my code. To this purpose, I'm clicking right button on mouse over the pin, and so I'm selecting Enter User Label. I would propose here LED_green and press Enter. Okay, we've got debug pins, so we've got our LED, green LED pin. We do not need anything else for the moment from this perspective. Let's have a look on the clock configuration. So this is the second tab. Clock configuration is over here. I just click it, and I can see the clock scheme of selected STM32G0 71 microcontroller. By default, all STM32 devices are clocked by the internal oscillators. In this case, it is HSI, so high-speed internal RC. Its frequency is 16 MHz. So this is the default clock source for the system, as you can see. We are not using any PLL and external components. This is just to simplify the application and make it easy to start. We will not change anything on this step. We will play with the clock configuration during our next hands-ons. Okay, let's go to the project manager to generate the code. As you can see from the project manager, we've got already specified the project name, project location. We've got as well the toolchain folder location and toolchain IDE. As you can see, there is no selection over here in the toolchain IDE, as we are running STM32CubeIDE, which is the combination of existing STM32CubeMX and CC++ environment. There is no option to change the toolchain. To generate the code, it is enough just to save the current project. As you can see here on the top, we've got a small star, which means that the file has been edited and it must be saved. So I just press Ctrl S, and I've got an information window whether I would like to generate the code. I just press yes, and the code is generated. You can see it on the left side of the screen. So here on the left side, you can see the project explorer for our project G0_lab. You can see some main components here, like drivers, source, startup, include, then IOC file, which is the device configuration file we just finished, and the linker file for the flash memory. Now we will open the main.c file, which is the main source file for our application. What we can see here is a template generated by our configuration tool. Within this, we can see the main function. We can see some set of configuration functions which are using the HAL library. So the next step we need to do is to perform this LED toggling. To control this LED, we will go to the while one loop over here. Please remember to keep your code within this user code, begin user code, and spaces. Otherwise, if you put it somewhere else, like in this line, which are just between those areas, your code would be erased during regeneration of the code or any modification done within the device configuration. Okay, so let's start with the coding. So the first thing we need to do is to find some function which would control our LED. As you remember, we are using the HAL libraries. HAL, let me remind you, it's Hardware Abstraction Layer. And all of the functions which are within HAL libraries begin with the prefix HAL. So HAL underscore. Then, if you would like to control some peripheral, we need to put its name. To control LED, we need to control GPIO, where we've got the LED connected. So the next point would be GPIO underscore. And if we don't know which function could be used here, we can use control space. Control space is looking within the library and it's displaying all the functions which are starting with HAL underscore GPIO underscore. It is a very nice feature implemented in Eclipse environment. It's speeding up the coding process. So from the list of the available functions, I would select this HAL GPIO toggle pin. And we've got two arguments here. One is the port and the second one is the pin. I can use here the name of the port, so GPIO A and then GPIO pin 5. But please remember that we have used label for the pin. It is LED underscore green. And if we use label, it should be visible as well for the coding. So let's use this label. LED underscore green, control space, and I can see two defines. The first one is port, the second one is pin. I would select the port, and on the second position I would do the same. LED, control space, LED green pin. The first thing is done, LED toggling. The result of the function would be toggling of a PA5 pin where our green LED is connected. To make it visible, we need to put some delay after. How to find the delay? Within the HAL libraries, we've got as well the dedicated function to make a delay. Let's try to find it. HAL underscore delay. As an argument, we need to put a delay value in milliseconds. I would put 500, so it will be half a second. And that's it. The code is done. Now we need to build it. To build the code for this project, we'll use the hammer button. It will take some time. We can see information about the output data. So how big is the code, how much data we've got, what is the output file name, what was the time used for the compilation. Our next step would be to run the debug session. Okay, let's connect our boards with microUSB cable. You should see this red LED on the right side of the top connector turned on. It means that the driver is properly installed and our board is properly detected by the system. Once the board is connected, let's try to run the debug session. For this purpose, we've got this bug icon over here. Just press it. Now we've got a selection, how way we would like to debug this application. We will select the second option, so STM32 MCU C++ application. Okay. Now there is a space to edit the debug configuration. We will not do any modifications here. So let's just press OK. And now we can see again the warning about the perspective switch. You remember it for the first time when we started this project, there was a warning about the device configuration perspective. Now we will switch again from C++ perspective for editing the code into the debug perspective. I would press switch with remember my decision, just not to waste time to click this window all the time. I will go to the debug session. The difference we can see right now is that we can see a bit different top bar, which has some buttons which allows us to debug the application. So start the code execution, so we can see the resume the code execution, we can see the suspend code execution, we can see terminate of the debug session. We can as well disconnect from the target. There are some components as well to go within the code. Let's just press resume to start our application. As a result, you should see green LED toggling, half second on, half second off. To stop, to disconnect from the target, you should press the terminate button, and now as a result you will come back to C++ perspective to continue the code processing. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this part, I will demonstrate how to create a project using STM32CubeIDE and HAL libraries for G0 family to use external interrupts to control our LED on board. The objective of this session is to properly configure I/O line to work as an external interrupt source and use it to control our LED. In this part, I would demonstrate as well how to configure the interrupt controller built in within Cortex-M devices. It is so-called NVIC, Nested Vectored Interrupt Controller. This is the block diagram of external interrupt module, which is built in within STM32G0 microcontrollers. As you can see on the left, this block is connecting all of I/O pins. We can have up to 5 I/O ports within STM32G0 lines. We can have as well some other sources, wake-up sources, events, which can act as an external interrupts. We will focus on usage of external lines coming from GPIO port C, because our blue button, which we will use as an external interrupt, is connected to PC13 pin. If you are interested in more details concerning external interrupt module, Cortex-M core details, you can refer to our online training dedicated to STM32G0 family. We will use in our exercise as well the green LED, which is connected to port PA5, and our blue button, which is connected to PC13. As you can see, we should detect the following edge of external interrupt. Let's start STM32CubeIDE project. I would use the same workspace like previously generated G0_LED to toggle LEDs. The first thing I would like to do is to close the current project. This is a very nice feature of an Eclipse, because if I close it, all of the files related to this project will be closed as well. So I just click on the right button on mouse and select Close Project. So now the project is still present in the workspace, but I would be sure that I would operate on the proper one. And all of the files related to these projects are closed as well. To open it, I just double click on the name and the project is open again. Okay, so let's close it and let's create a new one related to our external interrupts. To do this, I can go either to File, New, STM32 project, or I can use this icon over here. So New and STM32 project. It is starting with initialization of the micro selection, so we can select the microcontroller we would like to use. In our case, it would be G071RB, and we'll use this LQFP64 package version. I press Next. Now I need to specify the name of the project. In our case, it will be G0XT. I press Finish. Now the application will start the device configuration perspective. Okay, we can see our microcontroller. I can scroll wheel on the mouse to zoom it in. The first thing is connection of the debug interface. So I would go to System Core, Sys, Serial Wire. Then PA 13 and 14 would be dedicated for the debug interface, SWD. The second point is a configuration of our green LED pin, PA5. Left button on mouse and I select GPIO output and I would like to set the label on it. I click right button on mouse and I select Enter User Label. And I would select LED_green, Enter. And we need to configure properly the pin which is used by our blue button. It is PC13. I'm looking for this pin using this search window. PC13, it's over on the left side. Again, I click left button on mouse. I select the last option, GPIO XT13. You see that we see some warning within the sys peripheral, which means that system wake up 2 will be not accessible anymore because we selected this pin PC13 as GPIO XT13. If I would click once again on the left mouse button, we see here several functions which can be selected for this pin. One of those is system wake up 2, like it's visible on the left side of the screen. This is why this is highlighted right now on red, which means that this function would be not available anymore. Okay, let's come back to our pin. So we've got GPIO XT13. Let's add a label as well to this pin. So over the pin, I click right button on mouse. I select Enter User Label. I would select the name blue button. Enter. You can refer to those settings within main.h file. All the labels are stored there. Concerning the pins, this is all we would like to do. We do not perform any clock configuration modification. What we need to do as well is to properly configure this external interrupt input pin to be active on falling edge. How to do this? We will go to the System Core GPIO configuration. If I select PC13, I can see some additional configurations. GPIO mode, this is something which is important for us. I can see here external interrupt mode with rising edge trigger detection. This is the default setting. We will change it by scrolling down to interrupt mode with falling edge detection. We will not select any pull up or pull down, which is available on the pin, and will not change the blue button. The last point, which is necessary to be done to have active interrupt external line, is to enable the interrupt signal within interrupt controller. How to do this? We can go either within GPIO to the NVIC tab and just select enable, or we can go directly to NVIC settings and enable this signal on this side. Once it is done, this is the time to generate the code. The easiest way to do this is just to save the current project. So Ctrl S. We see some action is going. Right now the application is generating the code based on the selections, on the configuration of the device, of the peripherals we have just done within this perspective. Okay, the code is generated. We can go to the source files. So let's go to the main.c, and we can see here a lot of lines, a lot of comments, and sections like user code begin, user code end. This is the place where our code should be located in order to keep it in project regenerations. So what we need to do, so the first thing is to define the flag, the variable, which would be changed within the interrupt routine, and based on this value we will toggle LED or not. Okay, so let's scroll up, and we've got the section private variables. It's more or less line 47, and we will define the 8-bit value, which could be called flag with initial value set to 0. Next point would be to implement the LED toggling in case the flag is set. And set of the flag would be done within the interrupt routine. I would start with the if loop. If one flag, and now we need to toggle LED. So we are using HAL libraries. This is why this prefix HAL. Then GPIO and Control Space to select the function. I would select toggle pin. The first argument here is a port name. As I'm using labels, I would start with the label name, LED green. That's of the port, and the same for the pin number. I would select my labels, Control Space, and the pin. So within this function, I will toggle LED if the flag is set. Then we need to clear this flag afterwards. So the missing point is to create the procedure where we will set the flag. And the location of this procedure should be related somehow to our interrupt. How to do this? Let's go to the interrupt routines file, which is STM32G0 Let's scroll down. This is the file which contains all implemented interrupt routines. So at the beginning you can see some system functions like fault handlers, sysdig handler, which is used to generate the timeouts. And below, more or less line 145, you can see as well the external interrupt handler, which is called XT4215. In Cortex M0 Plus, which is the base core for this microcontroller, some external interrupts are grouped together, and our number 13 is within the common vector used from channels from 4 to 15. If you are interested in more details about the structure of this external interrupt peripheral, please refer to the separate online training which is available on our webpage. Now we will focus on handling the interrupt. So within the HAL library, once you generate the code using external interrupts or any other interrupts, this kind of the interrupt procedure would be generated automatically. And there would be only one function which is located within the HAL library. I would go to its location. It is located in a GPIO peripheral source file. And the role of this function is to select the source of the interrupt, clear the flag, and at the end call the proper callback. In our case, we will use the following edge interrupt, so we will call this callback. We should call this callback. Those callbacks are implemented within the library as an empty functions with weak attribute, which means that we can implement them as well in our code. And during the compilation, we should not receive any warning. This is the role of this weak attribute here. Okay, so I will just copy the name of the callback and its arguments into my code. Very good location for this is section user code begin for, which is below the main function. So I would put this function over here. So as you have seen, the flags concerning to the external interrupt are cleared by the HAL library. So the only thing is to implement some action which is necessary for us. And as you remember, what we need to do within the interrupt procedure is to set the flag. So I set the flag, I save the code, and I'm trying to build it. I click the hammer icon. It takes some time. At the end, I can see the size of the code, compilation time, and in case of any warnings or errors, those should be visible as well within this console window. Once it's done, let's start a debug session. For this, I'm clicking this bug. I need to select the way I would like to debug the application. I would select STM32 Mcu C++ application. I would not change anything in the edit configuration. This is why I press OK. Those windows would be displayed only during the first run of the debug session for the project. In the meantime, I can see the switch from the C++ perspective into the debug perspective. It is quite well visible because I can see the different toolbar. On the right side of the screen, I can see the window with possible visibility of the variables, breakpoints, expressions, and the registers within the micro. We will use it in the next sections. Okay, now we will just run the application. So I press the play button. And now if I press the blue button, on each blue button press, I can see the change of the green LED state. To exit this debug session, I just need to press this terminate button. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this part, we will use timer to control our green LED in so-called PWM generation mode. The objective of this session is to configure the timer in a PWM mode to blink the green LED to control it. So instead of using the software code, we will let the timer to do the job and toggle the LED. This time we'll use PA5 as an alternate function, and we will let timer to channel 1 to control it. Our system will work on an internal clock 16 MHz divided by 2 this time. So our system clock would be 8 MHz. We would like to keep the same timing like in previous exercises when we controlled green LED by software. To do this, we need a 1 Hz period with 50% duty cycle PWM signal. Let's start a new project with an STM32CubeIDE. I would use already existing workspace with previous exercises. To start a new project, I can go to File, New, STM32 Project, or directly to this icon and select STM32 Project as well. It is starting with the target selection. I'm selecting my microcontroller, so it is G071RB. I'm selecting the LQFP64 package, which is present on the Nucleo board we are using during this hands-on. Selecting Next. The next step is a project name. I would call it G0 PWM and press Finish. Now it is initializing the device configuration window, which is in fact the Cube STM32CubeMX application or plugin within Eclipse environment. It takes some time. As a result, we should see our G0 PWM IOC file, which is the configuration file, the file for the configuration of the microcontroller. I can zoom it out for better visibility of the microcontroller. You can use either those plus minus zoom buttons over here or the wheel on the mouse. Okay, the first thing would be the selection of a debug interface. So I will go to the system core, sys, serial wire. I can see PA 13 and 14 dedicated for debug interfaces WD. And the second thing is a configuration of our PA5 pin, which will be controlled by timer 2, channel 1. We can do it in two different ways. The first is by the selection of the timers. So I would select timers, timer 2. From this I would select the clock source as internal clock. I will not select anything from the slave mode nor trigger source, because we will not use any timer cooperation, timer synchronization within this library. So only the clock source as internal clock, and I would use channel 1 as PWM generation channel 1. Please be careful and do not select this PWM generation output, because it would generate PWM signal, but it will be not connected to the pin, but used internally. Okay, so we are selecting PWM generation channel 1, and it is automatically by default routed to PA0 pin, which is not our choice. To change it, I press Ctrl button on my keyboard and left button on mouse. And by clicking the left button on mouse, I can see the alternate locations of this function. I can see that one of those is PA5. So I'm keeping this control button and left button on mouse pressed, and I'm just dragging this PA0 pin roll to PA5 and releasing the left button on mouse and control button on the keyboard. As a result, I'm migrating my function, my timer 2 channel 1 location from PA0 to PA5. So this is one of the way how we can do it. The second way is a bit different. So please let me come back to the original setting. I'm pressing the left button on mouse and selecting I'm pressing left button on mouse, selecting reset state, and instead of selecting the role of on the timer, I'm going to PA5 directly and pressing left button on mouse, and I'm selecting timer 2 channel 1. I'm selecting timer 2 channel 1. Now I can see the pin over this button. Its label is changed to timer 2 underscore channel 1, and the color of the pin has changed from gray to yellow, which means that this pin is reserved, is booked by me, and it needs to be configured. To do this, I'm going to my timer 2 configuration into the mode window, and within channel 1, I'm selecting the role of this pin, which should be PWM generation channel 1. After this operation, I can see that the color of the pin has changed to green, which means that we've got this pin configured properly. So we've got configuration of the pin. The next step would be the configuration of the timer itself. Before this, let's do the short exercise on the clock configuration. As you can see, the default settings of the clock configuration is the following. We are using internal clock source, a high-speed internal RC, which is 16 MHz, and then this clock is going directly to the system, clocking all other peripherals. What we will do within this very simple exercise, we will change this 16 MHz within this high-speed clock on the bus to 8. I would just change this 16 value over here into 8 and press enter. As you can see, application automatically adapted its settings to my target value. All the system is now working on 8 MHz, including all the peripherals. Okay, let's come back to our application. So I'm switching back to pinouts and configuration. And now we will focus more on the configuration of the selected timer. I will do some space over here. Mode is already selected. We will not change anything. So the clock source, internal clock, and channel 1, PWM generation channel 1. Okay, so the configuration. Within the timer configuration, we've got quite a lot of fields which we can configure. In our case, we need to configure the timer to work in the PWM mode with the frequency of 1 Hz and duty cycle 50%. How to do this? We've got the input clock for the timer on the level of 8 MHz, so we need to divide it somehow. For this, we've got a few possibilities. The most convenient ones are the Prescaler. This is the first component we can use here. So we need to downgrade somehow this 8 MHz to smaller value. I would divide it first by 128. I put 127 because in the register settings there is one edit automatically to the value PSC which we've got in this field. This is why to have division 128 we need to put 127 in this field. Okay, so as a result, to the timer we will have instead of 8 MHz we will have 62,500 Hz as on its input. Then the counter will be up counting, and the second point we should configure is a period, so the value to which the timer would calculate. And how to do 1 Hz from 62.5 kHz. We need to divide this 62,500 Hz by 62,499, and again we are subtracting 1 from the value to be put due to the fact that we are calculating from 0. So in fact, as a result for this, we would create 1 Hz signal. So we've got 1 Hz. The only missing point is to set the duty cycle. The duty cycle we are configuring within the pulse, and its value should be related to the period value. If you would like to have 50%, we need to put half of it, so it will be 31,250. In this case, as a result of these operations, we would have on PA5 pin, which would reflect timer to channel 1, 1 Hz signal with 50% duty cycle. Now we are ready to generate the project, so I just press Ctrl S, Ctrl Save. Now we see that something is happening. Okay, let's go to the source. So I'm going to the sources, main.c, and again I can see a lot of user code, begin, user code, end sections, which are dedicated to my code to be protected against removal during the code regeneration. And what I need to do right now is to start the timer, because my generated application is only the configuration done by me, and I need to start the timer. We need to start the timer only once before while one loop has been called. So I'm using to this purpose user code begin to section. So I would start with HAL team, because it's for the timer, and I need to select the proper functions. As you can see, there are quite a lot of them, so I would just limit them by underscore. And let's select something which would generate some PWM for us. Okay, here there are some names, and we can see 3. The first one is just starting PWM signal without an interrupt or DMA configuration. Then there is as well start PWM start DMA or IT, which are using DMA or interrupt generation on its functionality. We do not use it. We will select PWM start function. The first argument is a handler to the timer we are using. Here you can see there is as well the information that we can select is timer 2 from our settings, and then the second one is a channel. We will select team_channel, and we can select the proper channel. Channel 1 is our choice. Okay, Control save to save the file, and now let's try to build it. So I press the hammer. Okay, and now we can start the debug session. So I press this back icon. I select STM32 C++ application. Press OK. I will not change anything in the configuration. I press OK. And now our application will be switched to the debug perspective. If you press Resume button, we can see our green LED toggling like before, but this time it is controlled directly by the timer. To exit from debug mode, we click Terminate. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this section, we will focus on the library's repository management. I would like to demonstrate to you how to configure properly and manage libraries which you are using during work with STM32CubeIDE. Let's start STM32CubeIDE. I would select one of already existing workspaces, which would contain at least one active project. Now on the screen we can see the workspace with 3 projects. One of those is active. This is G0_PWM. So let's start first with the configuration of repository location and internet connection. So to do this, let's go to Window, Preferences, STM32Cube. And from this set of settings, let's select Firmware Update. Within Firmware Updater, we can select the firmware installation repository. So this is the location of all CoolCube libraries which you are using during your development. By default, after the installation of this STM32CubeIDE, there is a quite long path selected. So I would suggest to select it according to your needs, to your preferences later on. Within this window, you can select as well the connection mode. Offline mode means that your application will not connect to the internet all the time, so it can work offline. Then check automatic settings. I would suggest to select the manual check, just to avoid any delay during the startup of the application, and select no auto refresh at application start, just to save some time during startup of complete application. You can check as well whether there is a proper connection of your application to the servers to grab data. So we can just press check connection. And if everything is okay, you should see this OK icon on the button. In case there is X button, X mark, it means that there is something wrong with the connection. Please have a look into these network connections and configure properly your proxy entries, if any. Proxy settings you can collect from your IT department. One important point within this firmware updater settings is that you can perform the firmware installation repository configuration only in a case if there is no active device configuration project. In fact, device configuration file. So for example, if I would open the IOC file for this project, and I will go to Window Preferences, you see, firmware installation repository is inaccessible right now, and there is a warning that we should close IOC editor. Okay, so I close it. I come back to this again, and now I can edit. Now let's have a look on the repository management. How we can add, how we can remove libraries, how we can update them. To do this, we need to go to Help and select Manage Embedded Software Packages. As you can see, at the moment it is inaccessible for us, which means that we need to open any of the IOC files to make our device configuration or STM32CubeMX application running. Okay, so now we see some IOC file opened. Now if we go to Help, we can see Manage Embedded Software Packages active. Okay, I select this option. And now I can see the new window, which contains two tabs, STM32Cube MCU packages, which is related to the Cube libraries for all STM32 devices. And there's another tab, ST Microelectronics, which contains some additional packages related to additional components coming from ST, like BLE sensors, MEMS sensors, NFC components. So those are the software packages which allows communication, which allows cooperation between STM32 devices and some additional components. We will focus on STM32Cube MCU packages, and let's go to the G0 section. I will just unscroll it. I can see at the moment, if I will scroll down, I can see that within STM32G0 there are 3 libraries available. Version 1.00, then 1.1.0 and 1.2.0. The most up-to-date one is 1.2.0, and this one is already installed in my repository. This is visible by this green square over here. I can download another one. I just press within the another square. This marking means that this library has been selected and can be installed now. To install this library, I need to go below and press this Install Now button. To remove the library, I need to mark it first. It will have this red X on it, and then I need to press Remove Now. Okay. Sometimes it is not possible to perform the installation of the library online. This is why it is possible as well to install the libraries offline using already downloaded zip files. All of the libraries are stored on ST servers as zip files. Those can be downloaded separately from the web, and then once you've got such a zip file, you can install it from this point using this From Local option. In this case, you are just selecting the location of this zip file, press Open, and it will be installed automatically. We can check as well the available updates on existing libraries on the tool itself. To do this, we need to go to Help, Check for Updates. In my case, there is one update available. I can check by using this refresh whether there is something new coming. There is no other update, so I can decide to install it just selecting this and press Install Now, or ignore it. I would select the second option. I will not use this library for a while. This Help Check for Updates is important if you select that within your repository configuration Manual Check for Updates, because it allows you to check whether there is something new, something more updated within the tools you're using in the time which is most suitable for you. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this part, we'll try to convert our existing example from HAL to Low Layer. We will reuse our existing external interrupt hands-on session, which has been fully done using HAL libraries, Hardware Abstraction Layer libraries, and we will change it to Low Layer. So in this project, we have configured already two GPIOs. One is output to control LED. The second one is an external interrupt, which is connected to our blue button on the port. We configured as well the nested vectored interrupt controller NVIC to accept interrupts from the external pin. But now we will reuse this configuration and transfer everything to low layer to check what is the difference between those two approaches. Okay, I have just opened STM32CubeIDE. I'm opening the project for external interrupts, and I'm opening G0 external interrupt IOC file by just double clicking to open the device configuration tool. The project is done, it's ready. We do not need to change anything within the pinout, within the clock configuration. So again, we've got the PC13 is configured as GPIO_external interrupt, line 13, and its label is blue_button. And then PA5 is configured as GPIO_output, and its label is LED_green. Additionally, we have selected SWD interface as a debug one, and we have not changed anything in a clock configuration. So we are working on an internal oscillator HSI 16 MHz, which is clocking the complete system. The only difference, which we'll do right now, is a difference within the project manager. We go to from project to the advanced settings, and for each of those two modules, RCC and GPIO, we will switch from HAL to low layer. I just click on this HAL and select low layer instead. The same for GPIO. Once done it, I will generate the code. So I just press Ctrl S, Ctrl Save. And now I need to regenerate the project. So I click this gear icon to generate the new project using low layer libraries. I can see some action on the left side. Now if I would go into the HAL driver, within includes I can see, instead of HAL files, I can see low layer ones. So the structure of the name for the file is the following: name of the family underscore type of the library, in our case low layer, underscore name of the peripheral. Most of the functions, in fact macros, to control the peripherals are stored in the header files as a macros which are operating on particular registers. The idea behind the low layer macros and functions is that each function, each macro, is operating on single register. Okay, let's have a look on our source file, main.c. Okay, we can see still this user code, begin user code, and sections. We can see still our flag, which was between the user code sections, so it was not deleted. Additionally, we can see some new functions like enabling the clock to system config and power. And we still can see our HAL function to toggle the LED because it was within the user code area. If I would try now to compile the code using the hammer, I can see two errors. If I would inspect it, I can see that HAL functions is not recognizable because we switched the library from HAL to low layer. I would comment it out, and then I will try to find a similar function within low layer library. So I'm starting low layer underscore GPIO underscore control space and underscore control space, and oh, there is exactly the same function, same name, toggle pin. And again, we need to specify the port and the pin mask. For this, I would reuse the arguments from above. Now it should be okay. Let me spend a while on definitions of those macros. we can find them within main.h file. As you can see, LED green pin has been transferred to LL_GPIO pin 5 and port is the same. If you would change to HAL again, those definitions would be changed as well. Instead, this LL_GPIO pin 13, we will have only GPIO pin 13 and GPIO pin 5. So the application during the code generation is handling on all of the definitions which has been developed by us during the device configuration. Okay, so we have the main while one loop ready. Next point would be implementation of the interrupt procedure. In the HAL version, we were using this callback, which would be not used anymore. So I would comment it out because the structure of the interrupts handling is a bit different here. So let's go to interrupt vector file when we've got all the procedures of active interrupts. And again, we've got some system ones like NMI, hard fault, SVC, PendSV, and SysTick. And we've got our IRQ handler for external interrupts. So as you can see, again, everything is done for us. I mean, detection of source of the interrupt and clearing the flag. But instead of calling additional function, everything is done within this this file. So we've got one call less in the hierarchy of the interrupt handling process. So the only thing we need to do is to set our flag set to 1, but we need to import it from our main file. This is why I will go here above this file and I would just import it extern. Okay. Now let's try to build it again. No errors, no warnings. And let's start the debug session. I press the play or resume button. And I'm pressing now the blue button. And each blue button is changing the state of our green LED. So the application is working properly. I terminate the code execution. And now application is still in Flash, so I can still play with the port. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this part, I would like to demonstrate to you some basic components concerning project management within the workspace, how the projects are organized, how to switch between them, how to switch to different workspace, what are the key features and which can help you on day-by-day development. So the objectives. We will demonstrate how to manage the projects within STM32CubeIDE. We will explore some project settings, basic ones, where to find the most important ones. I would like to demonstrate to you how to share the project with others using import-export features, how to switch to another workspace, and how to restore some default settings by resetting the perspective. So let's start from the beginning. Projects. Within STM32CubeIDE, as it is an Eclipse-based environment, we are working on a workspace which can contain one or more projects. Within the workspace, we can perform some basic operation on the projects. We can switch between them, we can make them active or disactive, we can close project, we can delete the project, we can delete the project as well from the file system. So all of those features are available. Let's start with the basic concept, project opening, project closing. As I told you before, only one project can be active at the moment. but many of the projects can be opened. There is a big risk that if you have opened more than one project and from each project you've got opened some files, it can be difficult to manage it. It may happen that you will edit some files from the project which is not currently active. It can create some mess. This is why there is a good feature within Eclipse, and it is available as well within STM32CubeIDE, which is closing and opening the projects. The feature which allows you to close and open the project. On the left part of the screen, you can see the example of the workspace, which contains 7 projects. One of those is open. This G0 LED is open. To close this project, it is enough to click on its name, then click right button on mouse and select Close Project. In this case, you will see the situation like in the middle of the screen, that all projects are closed. To open the project, it's enough to double click on the name of the project, and then it becomes an open and in the same time active. What is good is that once you click, when you close the project, all opened files which are related to this project are closed automatically. Here you can see it on the screen that we've got the main.c and the IOC file related to G0 LED opened. Once you select the close of this project, those files are closed as well. Here is a more difficult example when we've got 3 main.c files opened in the same time from different projects, and we've got 7 open projects at the same time. Of course, only one is active, but sometimes it's quite difficult to check which one or which main.c file is for which project. Just to make an order of it, we are selecting one project, just clicking on its name. Then we are pressing the right button on mouse and we are selecting Close Unrelated Projects. All other projects which are not this G0_LED are closed automatically together with all files related to those projects. Only one main.c remains related to this G0_LED, and we can continue the development. To switch between the project is quite easy. Within Eclipse and STM32CubeIDE, it is just enough to click with the left button on mouse on the project we would like to make active, and there will be automatic switch from one project to the other. How to check the properties of the project? It is enough to highlight its name. So we click on its name, then we click on the right button on mouse and select from the bottom of the menu Properties. In this case, a new window would pop up with title Properties for and name of the project, in our case G0_LED. And within this window we've got all the settings available for the project. Within CC++ build, we can select, for example, configure the parallel build of the application. So in case you've got the stronger PC, stronger multi-core CPU, you can select the enable parallel build and, for example, use optimal jobs, which are optimal for your application. Then within CC++ build settings, you've got all important settings concerning the tools which you are using to generate the code. So starting from the MCU settings, you can select the floating point unit which is used, instruction set which is used, runtime library, which is very important because it allows you to reduce the code which would be used by your application if you are not using all the features from the standard libraries. You can select, for example, nano library, which is much smaller and will not increase the code of your project drastically. So this is the MCU settings. Then from the next option, MCU post build outputs, you can select what kind of output files you would like to have as a result of the build of the project. So we can generate binaries, hexadecimal hex files, or Motorola S files. So those are the options. So you can as well display information about the size of generated code, and you can select or unselect the generation of the list file. Within tool settings, you can configure as well assembler, C compiler, and linker, which is used to build your application. So this is the place when you can specify the optimization level. You can specify some additional definitions which are used within the preprocessor. You can specify some additional include paths or some other components which are used by the compiler or linker or assembler. If you would like to share the project with others, or just store the project in some external repository, we can do it using export option, which is as well the feature of the Eclipse environment. To do this, we need to go within the workspace to File, Export. As a result, we will see an export window. From this, we need to select from General section either RHAV file, if you would like to store our project in a compressed form, zip or tar, or file system, if you would like to store the project in some folder. I will demonstrate the feature with RHAV file of zip, so general RHAV file. Then window will change and it will display all available, opened projects within active workspace. In our case, we've got 7 of them. We can select which projects we would like to export into the file, and then we need to specify the RHAV file. This is this window below. We need to press browse and select the RHAV name. Then we need to specify what would be the format. It can be zip, it can be tar. I would use a zip file, and then once you do all those operations, you need to press finish. Having this zip file, you can share it within other team members from your team, and it would be possible to import it from different workspace. To import the file within the workspace, you need to go to File, Import option, and from General you can select what would you like to import. Within STM32CubeIDE, you have an option to import an RHAV file, existing projects into Workspace, so the CubeIDE projects. File system, import AC6 system workbench for STM32 projects or Atomic True Studio project. In our case, we will try to import the same file we have just exported. So we'll select General, Existing Project into Workspace. Then we need to select either root directory if the project is stored as a file folder and not a zip, or if it's stored in a RHAV file, we need to select RHAV file and browse it. I can select interesting projects for me and then press the finish button. As a result, all of the projects are popping up in my active workspace. Another thing which is quite convenient within STM32CubeIDE, it's coming from Eclipse, it's switching the workspaces. We can imagine the situation that we are working on several projects or several workspaces, and to switch between them, it's quite easy. It's just enough to go to File and switch Workspace, and as a result you can see the list of recently used workspaces and the option Other, which allows you to select a different location of the workspace, which is already existing. Another important point once you're working with STM32CubeIDE is perspective management. The perspective is a set of windows which are used in the current step of the development. We can have three main perspectives within STM32CubeIDE. The first one is device configuration, which is very similar. In fact, it's based on STM32CubeMX device configurator. The second one is CC++ perspective, which is used to code development, its compilation, its build. And the third one is a debug configuration, which is used for the debug purposes. It may happen that once you are working on the configuration we are working on a perspective, you close too many windows, change the configuration in such a way that not everything is visible. It is easy to restore the default perspective view from the application by using window perspective reset perspective option, which would restore the perspective view to its default configuration. In this part, I would like to demonstrate projects management within STM32CubeIDE. So the first thing, I would like to demonstrate how we can manage projects within STM32CubeIDE workspace. Then we will explore a bit project settings, and I will demonstrate how to share the project with others using import-export features, and some additional points, some additional features which can be useful during your project development. Let's switch to the workspace. I would use for this demonstration purposes one of the existing workspace. It contains all of the hands-ons which are prepared for this CubeIDE basic sessions. You can find them in the training materials in a zip file as well, so you can duplicate. Here on the workspace you can see several projects. All of them are closed at the moment. To open the project, it is just enough to double click on it. And just double click on this G0_XTI. This project became opened and active. Active means that if I would press on it, I would press on the hammer, only this project would be built. Important point is that active open project can be exported later on. All closed projects are not handled within export operation, which we'll discuss a bit later on. To close the project, we need to click the right button on mouse and select Close Project. Important point is that when you close the project, you are closing all the files related to this project. I will demonstrate now this feature, just opening a few files, few projects. I opened 3 main.c files from different projects. It could create some problems during our development. What we can do here, we can use this close project feature. Let's assume the situation that we would like to continue development on G0_PWM project. What I can do, I can just click right button on mouse and select Close Unrelated Projects. Please have a look what it will be done. All the other projects has been closed, and all the files related to those projects are closed as well. Only main.c file from G0_PWM file is opened and can be edited. To delete the project, we just need to delete. Click on the project and press delete. It will be deleted from the workspace. But to delete the project, we just need to either click on right button on mouse and select delete, or just select the project and press delete button. If we just click OK the project will be deleted from the workspace without, and it will be not deleted from the file system. We can as well select this delete project content on disk, and then the project would be deleted physically from the disk. We'll skip this process, and now we will focus for a while on the project properties. If we select the active project, in our case it will be G0 PWM, I press the right button on mouse and select the last option, last position from the menu. It is Properties. A new window will be displayed on the screen. Its title is Properties for and name of the project, in our case G0_PWM. Within this window we can perform some configuration of the project, starting from selection how the build process should be done. If we are using multi-core PC, we can select enable parallel build and select the number of the jobs which can be done build process in parallel. So in my case it will be 4 jobs in parallel done during the build process. So this is the first point. Then within the settings, next option I would like to discuss is settings within the C++ build. Here in tool settings we've got complete set of the parameters used by the assembler, compiler, linker, but as well you can find here some settings about the MCU or post-build options which can be useful for your development. Within the MCU settings you can select the floating point unit which is used in your application. You can select the instruction set or runtime library. This last option is very important point, because you can select the reduced C library or standard C library. The difference is that in a reduced C libraries you have reduced functionality, reduced number of the functions or simplified functions, but the size of the standard library is much smaller, so the application in the final build will be smaller. So this is the first important point. The second option, MCU post-build outputs, allows you to select what kind of output files you will have after build of your application. You can have a binary file, Intel hex file, Motorola S-record file, or Verilog file. So you can select it. You can select more than one. You can select as well to display information about the size of the build project. It is done by default. And you can select on unselect generation of the list file. Then you have 3 main big sections concerning assembler, C compiler, and linker. Within those sections you can set some additional settings for those components. Most important ones are within the C compiler. So for example you can select the optimization level, which is by default none, so 0. You can modify the include paths, you can add something new, you can add some define symbols within the preprocessor, you can specify the debug level from none to maximum with the number of the information which would be generated during the debug session, available during the debug session. Those are the main settings which are available for the projects. Of course there are much more than this, but for the complete set you can refer to the manual for this tool. Next point I would like to discuss in this section is about the comfort of work within this environment. So what we can see right now on the screen is so-called C++ perspective. It is slightly modified by myself. So I already closed some windows. I can close more. And it may happen that during your development you click too much, you closed too much windows, and you don't know how to come back to the default state. For this you can go to Window, Perspective, Reset Perspective. Yes, and now as a result, current perspective will come back to its default default settings. Another thing I would like to demonstrate to you is how to export and import projects within the workspace. In our current workspace, we've got 2 open projects, the rest are closed. So let's select the export option. So I will go File, Export. I can select either archive file or file system or preferences. File system will store the project within the separate folder of the folder structure which is present in the project. I would select the archive file, which allows me to store everything in one single file, either zipped or tar format. I press next. As you can see, only open projects are available to be exported. I can select which of those I would like to export to the archive file. It can be in zip format, it can be in tar format. I would select zip. I would put it on the desktop. And now if I would go to the desktop, I can see one zip file with those 2 projects. It is possible as well to export particular projects from the workspace. I just click on the project to make it active, then I click right button on mouse and select export. And again, archive file, next. By default, there is only one selection of the file which I clicked on, and I can continue with exporting it to the to separate file. Let's call it like this, and finish. Okay, let's try to make an opposite operation. So I would switch to different workspace, to new one. So I would go to File, Switch Workspace, Other, and I would call it CubeIDE 5. It takes some time. The CubeIDE is restarting. Okay, it's restarting. Within new workspace CubeIDE 5, which we can see here on top, we'll close this information center, or I can click import project. As I exported all the projects within the zip file, I would use as an import source archive. I will go to desktop and I would select the first file, Mcu. You remember there were in fact 2 projects. I can click finish and I can see both projects on the screen. We can open previously exported projects a bit differently. Let me delete those 2 projects from this workspace. So I will delete it one by one. Okay, and now I would select from the file, open projects from the file system. Again, I will select archive, and select Mcu. Yes. And you see the effect is exactly the same. Thank you for watching this video. Hello, and welcome on our STM32CubeIDE Basics training session. In this part, we will focus on power consumption calculator. This is a part of STM32CubeIDE application, which allows us to estimate the power consumption of our application. To demonstrate this application, I would create a new project with an existing workspace. So I'll go to File, New STM32 project. So again, I'm going through STM32 target selector. We can do, of course, some estimation of current consumption for existing project, but in this case I would like to demonstrate something, some particular settings. Okay, so we select exactly the same microcontroller, G071RB. Yes, and LQFP version, I just press next. I would name it G0 PCC. All the settings are the same, default ones. Yes, CubeMX or device configuration perspective would be opened. Okay, so we've got empty project. Again, I would select serial wire as a debug interface. In our application, I would select as well RTC. Activate clock source with wake up. Activate calendar with a wake up capability, because I would like to demonstrate to you this power consumption calculator in connection with low power modes. So let's assume that we will use RTC with internal wake up. We will use as well PC13 in the configuration of system wake up 2 as well. And additionally, we will select ADC1 with some channels measurements. So let's select 2 channels, and from communication peripherals, let's select low power UART 1. In asynchronous mode, 9600 bits per second, 7, let's do 8 bits including parity. Without parity, 1 stop bit, the rest remains the same. For the clock configuration, I would keep the default settings. I would not focus much on the configuration, and I'm switching to power consumption calculator for this particular application. My idea is to demonstrate to you some typical application, low power application, which should perform some analog measurements from time to time, transmit some data over the UART, and wake up periodically using RTC auto wake up functionality or dedicated pin connected to PC13. Before we go further, let's save our application, Ctrl S. Yes, it will generate the code. And now let's switch to Tools and Power Consumption Calculator. We can start with VDD selection. It can be 1.8 to 2.4303.6 volts. Let's select 3 volts. Temperature cannot be changed. And now we can select the battery which we'll use to work with this with our application. So when I press select, a new window pop up when I can either add my own battery, which can be specified by me, or I can select already existing and defined batteries. I would select classical AA1. It's 1.5 volts. This is why I need 2 of those. I could put here 2 in series. I can increase as well the capacity in milli. I can put some of those in parallel as well. This application allows me to estimate how much time I can work with my application using specified set of batteries. Next point is a definition of the steps, so how the application will work. To do this, I select a new step. As a result, this kind of window is popping up. I select the power mode, so either run or any of low power modes. So usually at the beginning we are in a run mode to configure all the peripherals. And now I can enable all the peripherals which has been enabled by me within the pinout and configuration phase. I would select this. So as you can see, we've got ADC, GPIO-A, GPIO-C, low power UART and RTC. Having this, we can continue. So power range. Within STM32G0 we've got two power ranges, medium and high. More information about the power range available in the G0 family you can find on dedicated online training. I would select the range to medium, which allows me to limit the current consumption. So as we enabled all the peripherals which has been selected by us in the previous step, we can continue our evaluation. So power range we'll set to medium to lower the total current consumption of the system. Memory fetch type, we will use flash, standard one. The VDD is already programmed, the voltage source is battery. CPU frequency, we will use 2 MHz to lower the power consumption. Clock configuration, we will use HSI because we are using internal clock. And step duration, so how long we will be in this run mode at the beginning, I would set on 10 milliseconds. We can specify as well some additional current consumption which can be related to connected peripherals, connected chips to our microcontroller. So I would keep it like this without any additional points. We've got the step consumption more or less 500 microamps. I press add, and I can see on the screen right now the current consumption in time. So right now it is IDD by step, so this step only. We can see right now the current consumption within one step. If we will use only this step, we can count on our battery for 7 months, 22 days and 1 hour. Okay, but we discussed at the beginning that I would like to create a low power application. This is why I would add a new step. And within this new step, I would select the stop mode, stop 1. Stop 1 mode with active RTC only. And I would like to be in this state for 1 second without any additional current consumption. I'm adding this mode as well. And after this 1 second, I would like to be in run mode again. But before this, I would like to show to you right now how our consumption profile has changed. Please have a look. Right now we've got all 2 steps, run and stop, and we've got the average current consumption curve, which is on the level of 12 microamperes. Okay, so we create the next new step. So this time it would be wake up from stop. We cannot select run mode or sleep mode or other modes because we need to wake up from a stop mode. So this is quite automatic mode. So I just add it, and after wake up from stop, I can add run mode again. So new step, I'm selecting run, memory fetch from flash, and again ADC. I can enable all the peripherals from the pinout, but this time I would like to be in this mode only for 1 millisecond. With 2 MHz, clock configuration HSI, 1 millisecond, add. Okay, so we've got 4 steps. We can save the sequence, we can load other sequence, we can compare the sequence with the other ones, we can display the sequence as well. We can have a look how much time we can work on the batteries we selected. So if we keep this scenario like this, we can work with these batteries 13 years, 2 months, 23 days and 7 hours. Average current consumption is 12.7 microamps. We can select with different display of this profile. So for example, we can select IP consumption, so in split on IDCs and GPIO, UART, so all the peripherals we are using in microamps. There is a split on digital and analog part, which is important in components like ADC or reference voltage used by the ADC. We can select only analog, we can select only digital peripherals. We've got split between run and low power modes. So there are various number of display of the information. Then we can save it, we can print it for further use. What is good in this application is that this power consumption calculator allows you to estimate the current consumption of the application, how it is working, and all the data which are used within this application are taken from the datasheet. So in the real application, you can be sure that your data, your realistic data, would be very, very similar. So this is very good help if you would like to start with the new development and just check whether the selected microcontroller is appropriate or not to your application. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this section we will create ADC example using DMA transfers of the conversion results. ADC will be triggered by the timer events. For all of those actions we will use HAL library. We will start with launching STM32CubeIDE. We can use existing workspace or we can create a new one. And we will create a new project for STM32G071 microcontroller. I will create a new project within existing workspace. So I go to File, New STM32 project. To start with the target selection. So our microcontroller is STM32G071RB LQFP64 package, which is present on Nucleo board. Our project name could be, for example, G0 ADC DMA, and I would use C language, executable binary file, and project type STM32Cube. I would keep the rest as a default settings. Let's wait a minute till the device configuration would be started. Okay, we've got the device configuration window. In front of us there is our microcontroller and it's pin out. So let's start from selecting the debug interface. So I go to System Core, Sys, and serial wire. I can see PA13 and 14 selected as debug interfaces. Then let's select the analog channel. So I go to analog section, ADC1. I scroll down to select the internal temperature sensor. We cannot see any change on the pinout because it's internal. And I need to put some configuration for the ADC. So let's go to the parameter settings first, and let's select some basic settings. We will keep the clock prescaler to synchronous clock mode divided by 2. It means that our ADC would be clocked by the system clock divided by 2. Our system clock is HSI 16 MHz, which we can verify in a clock configuration. So this is our system clock, 16 MHz, and ADC clock mux. It is this one. This selector, it is used for the ADC clock. At the moment we can see that it's clocked by the system clock, and additionally we are dividing this clock by 2. It means that IDC would be clocked by 8 MHz, which is important to select the proper sampling time parameters. Let's go further. We need to set the sampling time for selected channel. We've got two sampling times, in fact. We can select two different sampling times for two different groups of channels which would be sampled. In our case, there would be only one channel which would use, for example, sampling time common 1. By default, there is a smallest possible value there. It's 1.5 clock cycles, which is far too fast for our temperature sensor. But to have the exact value, we need to go to the documentation of our microcontroller. How to reach documentation to our microcontroller? In the meantime, I have opened datasheet for our STM32G0 microcontroller. Let's try to find the proper value of the sampling time of our temperature sensor. For this purpose, we'll have a look into the electrical characteristics and operating conditions. Within this list, there should be one chapter concerning temperature sensors characteristics, like here. Within this chapter, we can see some basic characteristics of our temperature sensor. On next page, we can find the sampling time for this temperature sensor, which is set as a minimum 5 microseconds, which is the 5 microseconds. Having these 5 microseconds as a minimum sampling time requested for internal temperature sensor, and knowing that our ADC would be clocked by 8 MHz, we can calculate easily that we need at least 40 clock cycles of this 8 MHz clock to properly sample our ADC channel temperature sensor. Let's have a look which value would be the most proper one. We do not have 40 clock cycles, we've got 39.5, which is below this minimum value. This is why we will select the next one, so 79.5 clock cycles as a sampling time. We are leaving the sampling time common to not touched, as we will not use it. We will have only one conversion, which is the temperature sensor. And we need to specify as well the trigger conversion source. By default, it is software. We will change it to timer 2, trigger out, and we'll select one of the edges. We can keep it like this. Let's scroll down the rank 1, which is the information about our channel. So we can see it is one channel. Its name. It's a temperature sensor, and its sampling time. It's 79.5 clock cycles, which is the value we would like to have. We keep the rest of the parameters not touched because we will not use them. The next point would be to configure the DMA, which would be used to transfer the data from ADC to internal buffer within SRAM. So let's go to the DMA settings. There is nothing at the moment, so we click Add. Select the channel. There is only one DMA request, ADC1. We have more than one channel available because please remember that STM32G0 contains DMA MUX, which allows us to select different DMA channels for different peripherals. We've got a lot of possibilities here. Let's select the default configuration. The direction would be from peripheral to memory, because we will take the data from ADC and transfer them into the buffer within the SRAM. There would be only one DMA transfer, so let's keep the priority on the low level. We will use only a single set of the conversions, so let's keep mode normal. It means that after the last conversion, the DMA transfer would be stopped, and we will stop on the last component within the buffer. Data width, let's keep as a half word because we will transfer 12-bit data, and we would increment the address on memory side. The rest of the parameters we will keep not touched. So that's it for ADC configuration. Next step would be the configuration of the timer, which would trigger our ADC conversions. So let's go to the timers, timer 2, and let's select the clock source for this timer as an internal clock. We will not use any channels because we will use only time base, so the overflows of the timer to trigger the ADC and these ADC conversions. So let's switch to the configuration, and we need to set somehow the configuration of the timer to trigger our ADC with the frequency of 1 Hz. How to configure our timer to work with the frequency of 1 Hz on the output and trigger our ADC with this frequency. Let's have a look on the clock configuration once again. We see that our system clock is configured on 16 MHz, which is transferred to all of the peripherals. As we can see, our timer clock is as well 16 MHz. So we need to divide somehow this 16 MHz in such a way to have 1 Hz at the end. Let's come back to the pinout configuration, and we've got here few possibilities. I would propose the following technique. Let's use a Prescaler, which is 16-bit value, to divide the clock as a first step. So I would propose to divide it by 16,000. It is important to put here the value, which is the desired value minus 1, due to the fact that in the final calculation there is one added to the value stored in this PSC part of the register. After this operation, we will have as input clock to the timer, to its counter, 1 kHz. So we need to divide this 1 kHz somehow to have 1 Hz. To do this, we are using this counter period, which would be set to 1000. I put the value 999 due to the fact that we are calculating from 0. So after this, those two operations, our timer would overflow with the frequency of 1 Hz, which is the desired value. This is the first part of the configuration of the timer. So we will have a timer which would overflow in the frequency of 1 Hz. Second step is to configure the trigger output, TRGO pin parameters. So the next point is to select properly the trigger output parameters. So first we need to enable this master-slave mode to enable triggering another peripherals like ADC by this timer, and then select the source of this trigger output signal. So we will change this reset, which is default value, to update event, and on each overflow of the timer we will have a trigger pulse to start a new conversion by ADC. That's all operations within the device configuration. We can generate the code. So I can simply save the project, so Ctrl S. Yes. After a while, a project is generated. So we can go to our main.c file, which is the main file of our code. Okay, so we can see it is initially pre-configured. All of the peripherals we just configured within the device configuration are initialized. What is missing is a calibration of ADC, then its start and the final configuration of its connection to DMA, and then as a final step, start of a timer 2, which would trigger the ADC conversions. So let's do it step by step. Let's start from definition of the buffer we will use to store the ADC data. So the first thing would be the definition of its maximum size. So I would call it as ADC buff size, and I would set it to 8. Please have a look that I'm putting the code within the user code sections, just to be sure that after the code regeneration from the device configuration, my code would be not deleted. So the next step would be the buffer itself. The buffer will be used to store the 12-bit data. So we will use a 16-bit size of its basic component. And then let's name it ADC buffer, and its size will set to this which we have defined a bit before. Okay, so this is the first step, definition of the data, where we will store the temperature values. Okay, so next step would be to calibrate IDC. Calibration is needed to remove the offset error, and it should be run on each power on of the application. So just after the reset in our case. For this, we've got a dedicated function within the HAL. So if I would use HAL ADC EX, EX means extended. It is special marking for the functions within the HAL, which means that this particular function may differ from other similar functions on different STM32 lines. If you do not see an EX as a suffix in the function name, it means that this function can be copy-pasted across the families without any change. In case of ADCs, these calibration functions may differ from family to family. This is why we've got this EX suffix at the end. Okay, so we need to select the proper function, calibration start. Then the first argument, the only argument is ADC1 handler, and that's it. To be sure that this calibration has been done properly, I would check it. So I would check whether this function has been executed correctly. If it's executed correctly, it should return the value HAL OK. So I would use simple if, and then if, okay, so if it's not equal, it should execute the error handler function. This error handler function is automatically generated by CubeMX as well. You can find it at the bottom of this file. This function is defined as an empty function, so you can put here any action which would be triggered in case of any problems with HAL functions execution. Let's back to our coding. So our ADC is calibrated. ADC is calibrated. Then the next step would be to start ADC. So let's have a look for the options we've got. ADC start, and we've got three options. We've got start, start DMA, start IT. Start is for polling mode, start IT is with usage of interrupts, and start DMA is with usage with cooperation with DMA. So we are selecting this option, and we need to specify three arguments. The first one is handler to ADC we are using, so this is ADC HADC1. Then there is a pointer to the buffer where the data should be stored and length of this buffer. So the first argument is pointer, then there should be the buffer name, so ADC buffer, and its length. And again, it would be good to check whether this function is executed correctly as well. This is why I'm adding this part of the code. Okay, and the last operation to start the process is to start the timer 2. To start the timer 2, we need to execute the HAL function from a timer module, which would start the time base. Time base means that we are using only the counter and its overflows without any action connected to input or output channels. So in our case, we've got again start time-based start DMA, start IT. We don't care about the IT or DMA usage for the timer. So we are selecting the first function, the simplest one. The only argument we need to put here is a handler to this timer. So there is only one, timer2. And again, let's be sure that everything is correct with this function execution. This is why I'm adding this checkup. Okay, and we are done. So this is the basic piece of the code to start our ADC conversion with usage of DMA and triggering by the timer2. The source of the trigger has been done in the device configuration. In the code, we need to first do the calibration of ADC and then specify the buffer and its size and start both peripherals. Okay, so the missing point is to process the interrupt which is related to our DMA transfer complete. The interrupt call, it is managed within the STM32G0 file, where we will find DMA1 channel 1 IRQ handler. This function is automatically generated by the device configuration by STM32CubeIDE, and it is calling the function HAL DMA IRQ handler from our device. The HAL library is built in such a way that if we are using a DMI, usually it is assigned to one of the peripherals. There is a link created between DMI and the peripheral with which DMI is working. So in such a case, instead of calling the callbacks from the peripheral, in our case ADC, can be used instead. So what we need to do, it is defined within the halmsp.c file. If we go to ADC MSP init function, you can see that there is a configuration of DMA channel, and there is a macro called HAL underscore link DMA, which is connecting our ADC with a DMA handler, and it's connecting in fact the callbacks from ADC, which should be used normally by its interrupts, to callbacks with callbacks from a DMA. As a result, we can reuse for example, ADC conversion complete callback from ADC as a final result of DMA transfer complete. Knowing this, we can add the function within our main.c file. User code for a section is very good for this, and we are adding the new code. So HAL ADC conversion complete callback. And within this callback, we can either stop ADC in DMA mode or timer2 to not trigger ADC anymore. So I will stop ADC. So I'm selecting the function HAL ADC stop, and again we've got a DMA option, and ampersand and 1. I'm checking whether this function is properly executed. If not, I will call error handler. Okay, so this will give us only the option to early stop the ADC operations once the buffer is full. In the next step, we will try to post-process those data. So let's finish this project at the moment. Let's try to compile it. As a next step, we will connect our board and try to run the debug session. And let's observe what would be the result which we can gain in the IDC buffer. Okay, I have my board connected. The code is compiled. Let's try, after connection of the board, to run the debug session. So let's go to the debug session. I run it. The application will switch to the debug perspective. Now I can have a look on the buffer. As you can see, now I can have a look on its value, current value, the base address, the type of it. So at the moment it contains only zeros. Please remember that our conversion will last 8 seconds. We've got a buffer which size is 8 elements and the frequency of the trigger is 1 Hz. It gave us 8 seconds. To be sure that we are just at the end of the conversion, let's put our breakpoint in a callback, which would be triggered in case of DMA transfer complete. Okay, so I'm starting the execution of the code. Let's wait 8 seconds, more or less. Okay, execution is finished at the moment. So now we can have a look on the buffer. So we can, for example, highlight it in this area, and you see the values are not the temperature ones. We need to convert it to the temperature. Right now it's a pure reading from IDC, it's a raw value. It needs to be converted. For this we need a reference voltage value, which is in our case the power supply of the board, which is 3.3 volts. And we've got a special macro which can be used here to convert this value into the Celsius degrees. So now we will do this process. Okay, so the next step would be to specify the flag which would be used to highlight when there is a time to the conversion of the data. I would go into user code section for the private variable, and I would create one variable which is 8-bit long, and I would call it flag with initial value set to 0. Then I would set this flag within our DMA transfer complete, flag set to 1, and based on this value I would trigger the post-processing of IDC data within while one loop. So I would create here the if loop flag. So if a flag is equal to 1, we will do some post processing, and at the end, of course, we need to clear the flag to not do the same operations all the time. Okay, let's try to find a function which would convert our data. But before this, we will specify the index, which would be used to convert the data from the buffer one by one. I would use the simplest possible variable, 8-bit, because we've got only 8-bit data. IDX, I would set the default value as 0, and then we would create here the simple for loop. For IDX equal to 0, then IDX less than IDC buff size, and IDX plus plus. Okay, so we'd create a simple for loop. Let's find the function or macro which would convert our IDC raw data into the temperature in Celsius degrees. A lot of such functions are stored within low layer modules for given peripheral. So let's start from this underscore low layer, which is the common name of the macros, very useful macros to do simple operations. Then the peripheral name like ADC underscore and control space. We can see here interesting macro, ADC calc temperature. It looks that it is something we are looking for. As a first argument, it needs reference analog voltage, which has been used for the ADC. then the raw data from ADC and resolution we have used during our measurements. Let's have a closer look on this macro. So I would click right button on mouse and open declaration. So the first argument is analog reference voltage in millivolts. So I would define this name within my code in a section private defines over here. I have measured this value, it's 3.3 volts. In millivolts it would be 3300. And I would use this as a first argument of our macro. Okay, let's go to the second. Second argument is conversion data measured by ADC. So this is our buffer. Our buffer is, this is the name of our buffer, and of course we need a single element. So IDX, and the third argument was the resolution. We have used 12 bits, so I will select the resolution 12 bits like this. And of course we need to store the value in the buffer again. So we will just replace the old values, raw values, with the new ones in the Celsius degrees. Okay, let's try to compile the code. And start the debug session. Okay, let's, as a first point, let's remove the breakpoint from our callback. I already did it, so we don't need it in this place. We would need instead the callback in our while one loop on the place when the flag would be cleared, which means that it should be triggered once the conversion the conversion to the Celsius degrees is done. Okay, I double click on this line and I run the conversion. So first it would convert data from the temperature sensor, and then it will land into this part of the code and convert it to the Celsius degrees. Okay, we are already there. So I would just highlight our ADC buffer, and please have a look. Right now, instead of 900 something, we've got a value in the Celsius degrees. Please remember that this value is a temperature of the silicon of the structure within the microcontroller. It is not the ambient temperature, it is the structure temperature. This is why it can be a bit higher than what we've got in our environment. Okay, we can terminate the session, and that's it for this module. Thank you for watching this video. Hello, and welcome on our STM32CubeIDE Basics training session. In this section, I will demonstrate how to use USART to send the data and how to visualize it using the terminal, which is built in within the STM32CubeIDE tool. So the objectives of this part are the following. I will demonstrate how to configure the USART tool in asynchronous mode to send the data, and then how we can reuse existing connection between USART tool of our microcontroller from the Nucleo board to ST-Link, and then to use virtual COM port on PC to communicate with the micro. And then we will reuse existing built-in terminal application, which is a part of STM32CubeIDE. Let's start from STM32CubeIDE new project creation. I would reuse an existing workspace which contains already several projects. I would create a new one for our micro, so I go to File, New, STM32 project, and now I'm waiting for the target selection window. I'm selecting STM32G0 RB microcontroller. So it's enough to type G0 RB. This is this one, and we are selecting LQFP64 package version. So I click next, then the name of the project. I would propose G0 USART, and we'll select C as a target language. I would like to generate the executable binary type, and we will use STM32Cube and its device configuration to create the skeleton of the application. Let's click Finish to start a device configuration window, which is in fact STM32CubeMX, built in with an STM32CubeIDE complete environment. So we see on the left side that our new project is already created, G0 USART. It's an empty skeleton. So now we can see the complete pinout of our micro. Nothing is connected yet. So let's start from connection of the debug interface. So system core sys serial wire. We see that 2 pins has been already assigned. So this is the first point. Then we need to connect USART2, which is connected internally to the ST-Link. So we go to the connectivity, USART2, we select asynchronous mode, and then we see that PA2 and PA3 are assigned to USART2 TX and RX functions. And those 2 pins are connected to ST-Link on the ST-Link USART, and then are visible with a virtual COM port on PC once we connect our Nucleo board to PC. Okay, so we've got a connection to USART, and now we can configure our USART parameters. So let's configure the parameters. I would propose to keep 115,000 bits per second as a baud rate. Work length, it's including parity. I would use 8 bits, and let's use even parity. Let's keep stop bits to 1 as a default settings. We will not do any additional configuration, so we can generate the project. I will just save the projects by Ctrl S. So there is a question whether we would like to generate the code. I would click Remember My Decision and select Yes. On the left part of the screen we can see that our template is filled with newly generated source files. Okay, so now we need to go into the source and the main.c file, which is the main file containing the sources which are executed after the reset. And within the main procedure, we can see that we've got some initial configuration within the HAL init, then the clock configuration, which we kept as a default setting. So our system is clocked by HSI, so high-speed internal oscillator, which is 16 MHz. And then we've got initialization of the GPIOs and our USART2. What we need to do right now, we need to transmit in some area data over the USART. So to do this, I would use our while one loop, where I would put the function from USART domain. So HAL _ UART control space. And now I can see a lot of functions which are typical for G0 family, those with suffix EX, but I would select something typical, something easy. So I would like to transmit something without any IT, without any DMA, so I would select just simple HAL UART transmit. The first argument is a handler to the UART we would like to use, then the pointer to the data we would like to send, then the size of those data, and the timeout in milliseconds we would like to wait till the function will complete. So the first one it will be UART2. The second one, instead of the buffer, I would just specify the name. It would be test space, and the size it's 5 letters plus the end of the string, so it will be 6, And the timeout, let's put, for example, 100 milliseconds. Okay, to be sure that the function would be executed correctly without any errors, I would propose to check its return value. And in case of any trouble, let's call the function, which is already generated, its error handler. It can be called in all of the cases when the HAL function is returning value different from HAL OK, which is the proper execution of the HAL function. Okay, so I use if, then it's not equal HAL OK, then execute error. I will just correct the typing. Okay. To not block our microcontroller, I would use some delay function at the end. HAL delay. Let's put here 500 milliseconds to make this string display visible. Okay, so this is all from the coding side. Let's try to compile the code. So I would build it. Okay, and now let's try to run a debug session. I select STM32C application. This is the time I can change some configuration within the debug. I keep the default settings. And now I will switch to the debug perspective. Now we need to turn on the terminal window. And now, being in a console window, now we are in a debug perspective, so we can see the dedicated debug tab with resume, pause, so suspend and terminate debug session. In the bottom we can see the window with set of tabs. So console, registers, memory, outputs. We can set more registers, tabs, and important is to select the console window, console tab. If you do not see any console, you can go to the window, show view, and console. Within the console tab, you need to go to the open console and select common shell console. Then select serial port, select new, select many connection type. So I would select test G0, then a serial port which has been assigned to your Nucleo board. In my case it is COM31. Baud rate, like set in our configuration within the device configuration, so it was 115,000. Data size, it was set to 8 including parity, so I would set to 7 because we are using even parity, and the stop bits is 1. I click finish. I can select as well the encoding, one of the 3 options we've got here, but I do not use any special characters, so I use the default setting, and then I press OK. So I can see that my terminal is connected. Now if I run the application by pressing the resume button, I can see once per half a second the text I would like to display. Now I can disconnect the terminal just pressing this icon. I can connect it once again. It will continue. Please be careful once you disconnect the terminal and then you forget to close the console. Because in this case, if you try to create a new terminal application, it will be not possible. It will be not possible because there is already open connection on different name on the same serial port. Thank you for watching this video. Hello and welcome on our STM32CubeIDE Basics training session. In this module, I will demonstrate to you how to add the FreeRTOS middleware software to the project based on STM32 microcontrollers using STM32CubeIDE. So the objectives for this part are the following. First, we'll configure two IOs, PA5 as a GPIO output to control green LED, and PC13 as a GPIO XT13 to monitor the blue button, which is connected to the board. Then we will add the FreeRTOS middleware to our existing project, and within this FreeRTOS, I would add two tasks and one binary semaphore, which would be controlled by our blue button. Let's start with the new project on STM32CubeIDE. I would use an existing workspace when I've got already some ready projects. I'm creating the new project, so I go to File, New, STM32 Projects. It will start from the device selector. I'm selecting STM32G0 microcontroller, version LQFP64, which is used on our Nucleo board. I press next, and then name of the projects I propose G0 FreeRTOS. I select the target language as C, binary type executable, and we will use STM32Cube to the project type. I press finish, and now we will be switched to the device configuration window. Okay, so let's start from enabling the debug interface pins. So I go into the system core sys serial wire. I can see that both pins are selected as a debug interface ones. Second step is a proper configuration of our IOs we would use. The first one is PA5 when we've got our green LED connected. If I would put into the search PA5, I can see the blinking PA5 pins just to find it more easily. I press left button on this pin and I'm selecting GPIO output. Then I need to specify its label just to have a more easy configuration within the coding process. So I press the right button on mouse, selecting enter user label, and I would name it as LED green. The next step is a configuration of our pin connected to the blue button. It is PC13. So again, left button on mouse, and this time we will select GPIO XT13 because it would be an external interrupt. Please do not worry on this red highlight over here. It means that we have used this pin, so it will be not available for other functionalities like System Wake Up 2. If I would go with the mouse over this red component, I should see the information, what is the reason of highlighting this pin. There is nothing to be worried at the moment. We come back to our pin, and over this pin we click the right button on mouse and select user label. We will name it as a blue button. Okay, so this is the second component. So from hardware point of view, we configured all of the peripherals. So we go to the middleware, FreeRTOS, and we can select the interface. At the moment, for the G0 family, there is only CMSIS v1 library available. This CMSIS v1 means that over the original FreeRTOS API, we've got an additional layer, which is called CMSIS OS. So we select CMSIS v1, and within the configuration window, we can see a lot of new tabs related to FreeRTOS. First two, I mean config parameters and include parameters, are important because it's in fact creating the skeleton of the operating system, and it reflects the main configuration file within the FreeRTOS, which is freertos config.h file. Using config parameters, we can select the type of the kernel, whether it will use preemption or not. We can specify the tick rate, maximum number of the priorities of the tasks, then minimum stack size for the component. Please be aware that it's given in words. Then the maximum task name length, 16 signs. Then we can enable or disable some additional functionalities like mutexes, recursive mutexes, counting semaphores, tickless mode, which is used for low power applications. We will not change anything in this area. Important component is a memory management settings, where we are specifying the total RAM memory area which would be used for the FreeRTOS. Please be aware that this time it is given in bytes. So 3 kilobytes we've got at the moment, and the memory management scheme. We can select this memory management scheme from heap 1 to heap 5. We've got a dedicated session on the FreeRTOS within our channel, so you can have a look for more details on each memory management schemes. The most flexible one is in fact heap 4. If you would like to use the heap memory, which would be allocated on different RAM areas, please have a look on the heap 5 instead. It will be not our case, so I would select the most popular one, heap 4. Then the important point is the last two parameters. The first one is library lowest interrupt priority. Those two components are used to properly cooperate with the interrupts which are present in the microcontroller world. The first one, library lowest interrupt priority, is the lowest possible interrupt priority which is available in this particular microcontroller. As it is a Cortex M0 Plus, the lowest possible priority is 3. And this lowest interrupt priority is used for the interrupts related to the context switch and the tick interrupt used by the operating system. To be sure that all of the hardware interrupts are processed in proper way, operating system is operating on the lowest possible priorities, just not to interfere with hardware events. So this is the lowest possible priority for the system itself. The second parameter is used to set the maximum interrupt of the priorities, which can still execute the functions of operating system. Please remember that in Cortex M devices, lowest priority means highest number. So in this case, I would propose a small change. Instead of 3, we will put 2. So the task switching and the tick interrupt would have lowest possible priority, number 3, while interrupts which we would like still to execute the operating system functions would have interrupt priority 2. Other interrupts which we would like to be completely independent from the operating system will have interrupt priority 0. So in this case, all the hardware interrupts would be not interrupted by the operating system. So this is the basic configuration of the operating system. Let me remind you that all of the operations, all the configurations we are doing here would be stored later on in a FreeRTOS config.h file, which is the main configuration file of the FreeRTOS. The next file is used to include some additional functionalities, some additional functions to the operating system. This is used to add some additional functions to the operating system. The drawback of adding new functions is that we would use some additional code space. So if it's not necessary, we can remove some functions to save some code space. We will not use any additional new. We will keep everything as a default setting at the moment. The next point is to add 2 tasks. We go to the Task and Queues tab. At the moment we've got only one task. It is so-called default task, which is created automatically. We will change this default task to our task 1. Just double click using left button on mouse on this name and you should see the edit window. So we will change the default task name into the task 1. We will keep OS priority normal. We've got 7 types of priorities, starting from priority idle, which is the lowest possible, and ending with so-called real time. Normal is somehow in the middle, so let's use priority normal for both tasks. Stack size, it's set on 128 words, so let's keep it like this. Entry function, which is the function which would be called during the task execution. So instead of this start default task, I would use something different. Just task1_app from application. The rest I keep as a default. So this is the task 1, and I would add task 2, just pressing this add button. And again, I've got a new task, so I change the name task 2, priority normal, stack size the same without change, 128 words, and the function would be task 2 up. And okay, we've got two tasks defined with the same priority, with different functions which would be called during its execution. So this is the point number 1. Now let's add this one binary semaphore, which would be connected to our external interrupt triggered by the blue button. To do this, we need to go into the timers and semaphores tab, and we need to select the binary semaphore. So below this binary semaphore empty space, we've got the add button. So again, we need to add some binary semaphore. We will change this name into the binary underscore sem. Allocation dynamic. We've got as well in some areas static. If we configure the settings of the operating system, we can as well use the static memory allocation. Please have a look that, for example, in case of the timers and counting semaphores, we cannot add anything. Options are not accessible due to the fact that within the config parameters, we have not enabled those components. Please have a look. If I would come back to the config parameters and I would scroll down, and I would select use timers from disabled to enabled, and then come back to timers and semaphores. Timers became accessible. Okay, let me change it to disable again. Okay, so we are done with all of the settings of operating system from this device configuration window. Let's try to generate the code. I would just save the project, and please have a look. I've got a warning. Telling me that I should change the time-based source for HAL library from SysTick, which is the default setting, to some other timer. This is done due to the fact that SysTick is used by the operating system, FreeRTOS, as a tick timer. And it should not be mixed with the HAL library usage, because in HAL, SysTick is used to generate all of the delay functions and timeouts, and it should not be mixed up. Okay, so this is highly recommended to change the time-based timer for the HAL library. We can use it within the sys, system core and sys tab. And here at the last point, we've got the time-based source. I can select any of the timers which are available in the system. What I would recommend to you is to use either timer 6 or timer 7. Both of those timers contains only the time-based component, so they can generate the interrupt on overflow, and those timers do not have any input nor output channels, so the potential loss would be minimum in this case. I would select timer 6, and please have a look if now I would go into the timer 6, timers sections. I can see timer 6 inaccessible because it has been used as a time base for our application. Okay, let's try to generate the code once again. So I would I would just save the project. And now on the left side, we should see sketches. The project would be generated. We can see that middleware's folder has been added. If I would scroll it down, I can see the subfolder third party, then FreeRTOS source, and then below you can see the The main file is list.c, which is in fact the main file which contains the functions related to the scheduler, which is the heart, the core of the operating system. Then the semaphores and the queues are stored, the functions for these are stored within the q.c file. All of our tasks are stored within the task.c file. Timers is used for the timer semaphore. Then we've got additionally the stream buffer. We've got event groups to communicate between the tasks, and coroutines, which are not used in our architecture. Coroutines are used in 8-bit or 16-bit architecture and requires less resources from the embedded system. In our case, we will use a full version, so we will use tasks, so this file will be not used. So this is the core. It is completely independent from the embedded system, from the application, from the system where it has been added. The connection between our hardware, our STM32G0 and FreeRTOS is done within the portable folder. Here we can see GCC and memory management folders. In memory management folder, we can see only one file with the name which has been selected in the device configuration. And this heap_4.c file contains the functions to allocate and deallocate the memory, the RAM memory, for operating system components. So this is strictly related to the hardware. And then within the GCC, we've got subfolder ARM CM0. So it's for our core, which is the heart of our STM32G0. Inside we can see two files, port.c and portmacro.h. Those two files contains the functions which are connecting the interrupts from the real hardware with the functions from the operating system. So this is the real interface between the embedded system which we are using and the operating system we have just added. We will not modify any of those files. All of the modifications of the code which we will do should be done within one of the two files. The first one is app_freeRTOS and main.c file. If we go into the main.c file, we can see it as a standard CubeIDE or CubeMX generated file with some add-ons related to used operating system. So we can see within the private function prototypes, for example, the two functions which would be called when the task 1 or task 2 would be executed. So those names has been defined by us within the task configuration. Tasks add-on within the configuration of the FreeRTOS in a device configurator. So within the main, you can see that we're starting with HAL init, call configuration, GPIO init, and all the peripherals which we would like to init would be in this area. Then below, we can see the preparation of the components of the operating system which we have added. So for example, binary semaphore, tasks, and at the end of this process, we've got one single function to start the scheduler. It is OS kernel start. After this call, only the tasks which are active would be executed one by one, and we should never land below this line. If we land below this line, we've got some problems with the RAM memory allocation. If we go below, we can see both task application functions defined as empty functions with infinite loop inside, because tasks functions should be defined in such a way that it contains the infinite loop inside as a mini main functions. This is how it looks like, and now this is the time to add some code modification into our generated code. Now let's back to the NVIC settings. Before we will generate the code, let's have a look on the NVIC, so interrupt configuration. So within the system core NVIC, I can see some new settings. So I've got a new column over here, uses FreeRTOS function, which means that I can select which interrupt would be allowed to call the functions of our operating system. As we can see from this configuration, the lowest possible priority, so number 3, is assigned to 2 interrupt procedures. The first one is a system tick timer, so sysTick, which is used to generate the tick interrupt, and the second one is a pendable request for system service, so pendsv, which is used to switch the context from one task to the other. Both of them have the lowest possible priority to do not interfere, to do not block any hardware interrupt within the embedded system. Some of the interrupts have the priority number 0, as you can see. Those are very important ones and should not be blocked by the operating system. So we've got non-maskable interrupt, we've got hard fault interrupt, we've got as well time-based interrupt coming from timer 6, which would be used by the HAL library. The rest of the interrupts has been set with the priority number 2, which means that it will be possible to execute the operating system from those interrupt routines. It is visible on this last column over here. If I unclick this, the interrupt priority would change immediately to 0, which means that this function would be above the operating system, and this interrupt routine should not interfere with the operating system. I would change it once again. And what we are missing here is, in fact, enabling the interrupt from our blue button, so XT line 13. I'm enabling this. Its priority is 2, so it means that we would like to execute functions from the operating systems from this interrupt. Okay, now we can generate the code. Okay, so let's come back to our coding and let's change the default task application functions. Within the task 1, we would like to turn on green LED and then go to the blocked state for 1 second. So I would go to this for loop and I would just set the green LED to the high state. Right pin, and then we've got LED green port, then the pin LED green pin, and the pin state GPIO pin set. So this is turning on our green LED, and then we will wait for 1 second. Please have a look that I'm not using HAL delay but OS delay. The difference is that HAL delay would block us for 1 second within this function, while OS delay is changing the state of our task from running mode to the blocked one, which allows operating system to switch to the other task, which has some job to be done within this time. So this is not wasting any time. Operating system is immediately changing the active task from our, which is going to blocked state, to the other, which is much more efficient. So this is the step number 1. Step number 2 would be to do the similar operation with task number 2, but in task number 2 we will just switch off the task, the LED, and this time we will do some modification of OS delay, just not to be the same time. So I'm switching it off and waiting for some time. Come back to GPIO configuration. After configuring the GPIOs and its mode and labels, let's have a look whether we've got the proper configuration of external interrupt input. By default, it is configured as an external interrupt mode with rising edge trigger detection, while in our application the blue button is connected in such a way that it should be active on a falling edge. This is why we need to change it to external interrupt mode with falling edge trigger detection. we will do the following modification. Instead of using OS delay function within the task 1, we will go into the blocked state waiting for the semaphore. So I would comment this line, and instead of this, I would wait for the semaphore. So I would use the function OS semaphore control space, and then wait. We've got the binary sem handle semaphore and milliseconds. I would use here the value OS wait forever. OS wait forever is in fact, if we have a look, it's in fact the maximum value for 32-bit variable. And how it is working. This function is sending our task into the blocked state, inactive blocked state, for the time till the semaphore will be released, or the timeout will elapse. In this case, it will be quite long. This is why this is OS wait forever. So we will wait till the semaphore would be released. And where we should release the semaphore. To release the semaphore, we need to go for a while into the G0_ITC.c file, where we will find the external interrupt routine for our microcontroller. I can find this function within the HAL GPIO.c file, and I can see that a HAL library is clearing all the flags, and then once the flag is cleared, is calling the proper callback. As we are working with this external interrupt on falling edge, this would be the callback which should be used by us. It is defined as an empty function with weak attribute, so we can redefine it within our piece of code. I would copy paste it, and within the main.c file, in this user code begin for user code end for, I would use this callback. Then we can check whether it was exactly the pin we were looking for called. So I would put if, and then I would use this blue pin label. So if our variable, so GPIO pin, has been this blue button pin, I would release the semaphore. So OS semaphore control space. So we need to release the semaphore. It's like with the traffic lights. Release the semaphore means that I'm giving something, yes, which can be reused afterwards by other component of the operating system, like task 1. So the only argument here is a handler for this semaphore, this one, and that's it. One more thing on this point. Using this callback, executing code within this callback is still done within the interrupt routine of external interrupt from line 13. This is an important point because please remember that our hardware interrupts should not interfere with the operating system. The cooperation between hardware interrupts and operating system functions should be done in a careful way. The big advantage of this CMSIS layer is that the CMSIS library is taking care of selecting proper function if we are calling the operating system function from the normal code or from the interrupt routines. If we have a look into this function, this in CMSIS OS.c, not .h, it is coming, unfortunately, to the header file, not. We see that it is checking at the beginning if we are in a handler mode, so in the interrupt routine, or we are in a normal code. From interrupt routine, it is calling a different FreeRTOS API function with from ISR suffix, which is checking whether there was any component, any task woken up by this event, by this semaphore, and if yes, it is checking whether there is a need to change the context to different task which has been just woken up. So this is an important point, that using CMSIS OS layer, we don't need to take care about selecting the proper function. It is done automatically by the API. Okay, so coming back to our code, we have just added this semaphore. Let's try to compile the code. So now the task 1, which is responsible for turning on the LED, would wait for the semaphores for the which would be released by the pressing the button. In the meantime, only the task 2, which is turning off the LED, would be active. So now if I will go into the debug mode and run the code. Okay, so we will switch timer stick to timer 7. Please have a look that timer 7 disappeared from available timers. And now if we save and generate the code, we should have a new file, STM32G0 HAL time-based time, which contains the functions to suspend tick, resume tick, all the functions which are used by the HAL library to generate the timeouts and delay functions. And now if we compile the code with semaphore added, in the meantime we can have a look on interrupt TSC routine. We see that timer 7 IRQ handler has been added. We go to the debug mode, I start the application. I can see my LED turn on for a while and then turn off because the timer, the task 2 is only active. Task 1, which is turning on LED, is not active, waiting for the semaphore, which can be given by the interrupt triggered by the blue button. I press the blue button and for a while the green LED is turned on and then turn off because task 2 is taken into account. So that's it for this exercise. Thank you for watching this video.